Hey students, welcome to the video. Today we will talk about the bipolar junction transistor. Transistors are revolutionary devices which form the basis of integrated circuits, using which the modern day computers are possible. The bipolar junction transistor, or a BJT, is a three-terminal device. It can act as a conductor or insulator based on the applied input signal. Bipolar word suggests that both the electrons and holes are responsible for the flow of current in this device. This device can be used as a switch in digital circuits or as an amplifier in analog circuits. Although the field effect transistors, or FET, are more widely used in electronic industries these days, BJTs are still in use as well. Let's move on to the basic structure of the BJT. So basically, BJT comprises of three different doped regions. They are semiconductors, obviously. These three regions are termed as the emitter, the base, and the collector. There are two types of BJTs possible. In NPN transistors, the emitter and collector are doped with N types impurities, and the base is doped with P type impurity. On the other hand, in the PNP transistor, the emitter and collector are doped with P types impurities, and the base is doped with N types impurity. In a bipolar junction transistor, there are two PN junctions. It appears as if two diodes are connected in series, something like this. But it does not work the same as this. This is because in the case of the diodes, both of the diodes work independently to each other. But in case of the transistor, there is certain interaction between the three regions. So let's study in more detail about it. The emitter region is highly doped. Its function is to supply electrons. The collector is moderately doped, and the base is lightly doped. In terms of width, the collector has the highest width, then comes the emitter, and the base is the narrowest one of them all. Let's move on. Depending on biasing, the BJT can be operated in three regions. The regions of operation are: first is the active region, second is the cutoff region, and third is the saturation region. The active region is used basically for amplification, and the cutoff and saturation regions are used when the transistor is to be used as a switch. As discussed earlier, there are two PN junctions in the BJT: the emitter base junction and the collector base junction. In the active region, The emitter base junction is forward bias and the collector base junction is reverse bias. In cutoff region, both the junctions are reverse biased. In saturation region, both the junctions are forward biased. These statements are true for both the NPN and PNP transistors. Now let's move on to the symbols which can be used in making circuit diagrams of the transistors. So this is how in a circuitry the symbol of the transistor looks. This is the base terminal, this is the collector terminal, and this is the emitter terminal. In case of an NPN transistor, the direction of current is from the base terminal to the emitter terminal, which is shown using an arrow like this. Whereas in the case of the PNP, this direction is opposite, so a reverse arrow is used. Now let's talk in further detail about the active region of operation. There are three different configurations which can be applied in the active region. It depends on the terminal which is common to both input and output. There are three types of configurations. They are common base, common emitter, and common collector configurations. In common base configuration, the base terminal is common between the input and the output. This is the emitter, this is the collector, and this is the base. The base terminal, as you can see, is the common terminal over here, and the input is measured between the base and the emitter, and the output is measured between the base and the collector terminal. In case of common emitter terminal, it's the emitter which is common between the input and the output. So as you can see, the connections are made in such a way such that the emitter is common here. The input is taken between the base and the emitter, and the output is taken between the collector and the emitter. Similarly, in common collector, the circuit will go something like this, and the collector stands between the input and the output terminals. Both of them have the collector. Now let's move on to understanding the working of BJT in the active region using common base configuration in NPN transistor. So this here is a circuit diagram of a common emitter configuration in an NPN transistor. So for the symbols, for the base and collector supplies, same subscripts are used twice. For example, VBB is used for the supply that's connected to the base terminal, and VCC is used for the supply which is connected to the collector terminal. The voltage VBE is the voltage between the base and the emitter terminal, and the voltage VCE is the potential drop between the collector and the emitter terminal. So basically, VB equals VB minus VE, where VB is the voltage at which the base terminal is. So this voltage is VB, and the voltage of the emitter terminal is VE. Similarly, the voltage of the collector terminal is VC. If we write VC, then what we mean is VC minus VE. However, if we are writing VEC, then we mean VE minus VC, which is basically the opposite of VCE. So this is how the symbolism works. Now, in this case, the biasing is done in the active region. This basically means that VBE is a positive quantity and VCB is also a positive quantity. Whenever the base emitter junction is forward biased, the typical voltage drop across the junction is 0.7 volts. So this means that VB is inherently 0.7 volts when we are working in common emitter configuration in the forward bias. So let's dive into the working of the transistor after the biasing has been done. So the heavily doped region over here is the emitter. There are more number of electrons in the emitter which on biasing gets pushed towards the base region. Once the electrons are inside the base region, then they have two pathways. One is towards the left, towards the resistance RB, and the other is into the collector. Now most electrons move into the collector region because the base is lightly doped and it is very narrow, which means that the number of holes which can combine with the electrons is less. Hence, most of the electrons can escape from the base region into the collector. If you notice, when the electrons enter from the emitter to the base, they become minority charge carriers, and the base collector junction is reversed bias. Therefore, they are attracted by the collector region. From the collector, the electrons are attracted by the positive terminal of the VCC supply voltage. Hence, we can see that most of the electrons will flow in this direction and very few of the electrons will flow in this direction, which makes the base current extremely low compared to the other currents in the circuit. The direction of current is opposite to the direction of electrons. So we'll now show which direction the current is going in. So basically IB is going in this direction, IC is in this direction downwards, and IE is similarly in this direction. That IB plus IC equals IE. The base current is very small compared to the collector and emitter current as discovered earlier. So this can be neglected in some cases. For now, let's say that IC is equal to alpha times IE. From Kirchhoff's law, we can say that IB plus IC equals IE. IC is equal to alpha IE. Let's say that where alpha is a quantity which is equal to IC by IE, thus determines the fraction of electrons emitted by the emitter which the collector has collected. Now, if we substitute the values of equation 2 into the first equation, then we get IB plus alpha IE is equal to IE. This implies IB is equal to 1 minus alpha IE, and IE can be written as IC divided by alpha. So we can write IB is equal to 1 minus alpha times IC divided by alpha. Now this implies that IC is equal to IB into alpha divided by 1 minus alpha. This quantity, if we term as beta, then beta is basically equal to IC by IB. Now again, IC plus IB is equal to IE, which was our first equation. This means that IB plus beta IB is equal to IE, like we just discovered. This implies IE is equal to beta plus 1 into IB. This is the relation between the emitter current and the base current. In this common emitter configuration, this base current is the current in the input side and the emitter current is the output current. So beta equals output current by input current, which is nothing but the current gain. We can say that basically the input current IB is getting amplified by a factor of beta and it's getting converted into the higher degree of current, which is IC. Since IC is equal to beta IB, we can say that by controlling the input current, we can control the output current. This is why bipolar junction transistors are called current control devices. On the other hand, field effect transistors, which we will study in later videos, is a voltage control device. Now, up until this point, we haven't considered the current due to minority charge carriers in the collector region. So let's talk about that. If we remove or break this emitter connection from here, then the current that flows through the transistor is only due to the minority charge carriers. This current is called ICO. It is similar to the reverse saturation current in PN junction diodes. So the total collector current, that is IC total, it is equal to ICO plus IC. IC being the collector current which we talked about earlier, and ICO being the current when emitter is not biased at all. Typically, uh, this ICO is in the range of microamperes and IC in the range of milliamperes. So in certain cases we can just neglect the ICO completely. So friends, this is it for the basic idea of the working of BJT. I hope it was useful. See you all in the next video.